Today, we're going to continue looking at sequences, series, and power series. Yesterday, we established a necessary but not sufficient condition for convergence. We're going to focus on the convergence of series for a little while. And we're going to establish a bunch of tests that will help us identify quickly whether a series converges or diverges. Yesterday, we did the big one. We established the necessary but not sufficient condition for convergence. That is, if the limit of the terms is not zero, then the series diverges. If the limit of the terms of a series is not zero, then the series diverges. The contrapositive of this statement says that if a series converges, then the limit of the terms must be zero. It does not tell us that if the limit of the terms is zero, the series converges. That would be too easy. So that's what I mean when I say the limit of the terms being zero is a necessary but not sufficient condition for convergence. All right. So what we need to be able to do is look at a series, see that the terms go to zero, and then find out how they go to zero. That's going to be the big question. It's not about that the terms go to zero, it's how the terms go to zero. The limit of the terms can be zero, and a series can still diverge. So once again, what we get is the contrapositive. If a series converges, then the limit of the terms is zero. That's the contrapositive. Whenever you get a statement, if A then B, you always have the contrapositive. I was going to look up whether that is the contrapositive. I can't remember what if A then B. I can't remember the name for if B then A. So that you get if A or A if and only if B. But we don't get that one. So if the limit of the terms is zero, the series could converge or it could diverge. If the limit of the terms is zero, the series might converge or diverge. We have to develop some ways to determine this. So let's talk about some ways to determine this. We're going to start with the most grindy one. The integral test. So even though a series is a series, it's a function that's being evaluated just at integers. We're going to apply this continuous technique to determine if a series converges or diverges. So let's let AN be a series. All these tests are going to start off with one or two series that we're trying to start off with one series, and we're trying to determine if that series converges or diverges. So let's let AN be a series. First, let's make a function, f of x. Just take the terms of the series and make a function out of it. If the improper integral from 1 to infinity of f of x dx converges, then the series AN converges as well. similarly diverges. If the improper integral, say from 1 to infinity of f of x to x, diverges, then the series diverges. The integral from 1 to infinity of f of x dx is an improper integral because this function says find the antiderivative, then plug in infinity, which should set off the bad language alarm. We don't get to plug in infinity. Infinity is not a number. But this thing here is called an improper integral. So the integral from 1 to infinity of f of x dx is an improper integral. We can still evaluate the limit. We can still evaluate this integral from 1 to infinity. We don't plug in infinity because infinity is not a number. We plug in infinity by doing the calculus thing to plug in infinity. We just replace the infinity with a limit, say as b goes to infinity. So to evaluate the integral from 1 to infinity of f of x dx, we take the limits as n goes to infinity. Let's say b goes to infinity of the integral from 1 to b of f of x dx. This is how we plug in infinity in calculus. We don't write that we're plugging in infinity. And that would be a convenient notation. But the pedantic side of us is like, oh, well, we can't do that. That would be improper. So we can't just plug in infinity. But this does give us a way to evaluate these improper integrals. But I do want to point this out. This is how we plug in infinity. See, my dog doesn't like it. He's like, dude, you can't plug in infinity. It's not proper. So let's take a look at an example. This is an important series. This is called the harmonic series. The series 1 over n diverges. So this would be the series 1 plus a half plus a third plus a fourth forever. This is called the harmonic series. This is an important series. We have to recognize that this series diverges. This sum is infinite, even though the limit of the terms is 0. So notice that even though the limit as n goes to infinity of 1 over n is equal to 0, the harmonic series diverges. even though the terms go to 0, the harmonic series diverges. We can apply the integral test to this series by looking at the integral from 1 to infinity of 1 over x dx. So if we look at the integral test, or if we look at the improper integral from 1 to infinity of 1 over x dx, to evaluate this improper integral, we have to take the limits as b goes to infinity of the integral from 1 to b of 1 over x dx. Now we can find the antiderivative. The antiderivative of 1 over x is natural log of x. We're evaluating from 1 to b. We still have not taken the limit as b goes to infinity, so we still have to write the limit as b goes to infinity. Now we can plug in the endpoints. We still haven't taken the limit as b goes to infinity, so we have to write the limit as b goes to infinity of the natural log of b minus the natural log of 1. So in this case, the natural log of 1 is equal to 0, so that's convenient. And the natural log of b, as b goes to infinity, this term will go to infinity. I thought I was going to write another step, but I wasn't, so I don't need this equal sign. This limit goes to infinity. That is, this limit does not exist. Since the improper integral diverges, the series diverges. If you want to cite your sources, the improper integral diverges, therefore the series diverges by the integral test. Now we have a nice ironclad court case. Judge Judy will not throw us out of court, and she will not make fun of us on television because we have made our case. So one of the things I like about the integral test is that it gives us a clear border between what converges and what diverges in this context. What we don't like about the integral test is that we have to do an integral. And because you were like, oh, I thought we left all this stuff behind. And I'm like, oh, no, there's still the final coming up. What are you talking about? After the final, of course, you can leave your integrals behind, except for those of you going on to the Calc 3. Then you're going to have to hold on to your integrals for a little while. Right now, I'm looking really surprised. This is supposed to say equals 0. This is not exhibiting surprise at the natural log of 1. So just to clarify. So this is actually something we can visualize. Let's visualize the integral from 1 to infinity of 1 over x dx. So the integral from 1 to infinity of 1 over x dx is the area under the graph of 1 over x and above the interval from 1 to infinity. So we can visualize that. So if we draw the graph of 1 over x, from 1 to infinity. So the area, we know that the definite integral tells us the area under a curve. So we know that the area is the integral from 1 to infinity of 1 over x dx. We're going to imagine approximating the area with a delta x of 1. So what we're going to do is we're going to evaluate at 1, 2, 3, and 4, and 5, and so on. And we're going to do this forever. So evaluate the function at 2, and then at 3, and then at 4, and then at 5. And in typical fashion, we're going to assume that the function is constant for the delta x. So I'm going to say that the function is constant at 1. And so the area of that rectangle is 1. And then from 2 to 3, I'm going to use the 1/2. And the area of that rectangle is 1/2. And then when x equals 3, I'm going to assume the function is constant. We're just doing a left endpoint approximation. And what we're going to notice is that the left endpoint approximation of this area with the delta x of 1 is going to give us the harmonic series. The left endpoint approximation of the area is the harmonic series. The left endpoint approximation of the area with a delta x of 1 is the harmonic series. So we got a 1, then a half, then a third, then a fourth. Notice that the harmonic series is an overestimate of the area under 1 over x above the interval from 1 to infinity. So notice the harmonic series is an overestimate of the area. Also notice that when we calculated the improper integral said this area was infinite. So furthermore, the improper integral showed that this area is infinite. So we have an overestimate of an infinite area, and that tells us that the harmonic series must also be infinite. So we have to conclude that the harmonic series must also be infinite because it is an overestimate of an infinite area. I guess kind of means they're the same, but that's only because they're the same kind of infinity. Yes, this is the Toy Story result. To infinity and beyond. We could notice that if we did a left endpoint approximation, we would just be one less. If we had a half plus a third plus a fourth, we would get that if we did a right end approximation. And that would mean that the harmonic series minus one is an underestimate of the area. This tells us nothing, because all we're able to say there is that the harmonic series minus one is less than infinity. That is not helpful. So we don't, that's the reason that I picked the left endpoint, because I wanted an overestimate. I wanted to show that the harmonic series is an overestimate of something that we can calculate to be infinite. And it does no good to say that the right endpoint approximation would be an underestimate of this area, because that just concludes the harmonic series is less than infinity, and that doesn't mean anything. Because less than infinity could be finite, or it could also just be infinite. In this case, we can see, because of the conclusion with the left endpoint, we can see it would just be infinity minus one, and infinity minus one is still just infinity. Despite what your little brother said when you got into that nuh-uh, yah-huh argument, and you were like all nuh-uh infinity, and he was like all yah-huh infinity plus one, because that's the same. Because at that point, you'd be like, well, nuh-uh clearly wins because infinity plus one is still just infinity, so I guess I win, since you had nowhere to go. Now, if he was like all yah-huh uncountable infinity, oof, now you're stuck. Now you may have to concede. At that point, you should just call him, well, you're a stinky doo-doo head, and then you can walk away. Your little brother may have won the argument with his uncountable infinity of yahans, but you did declare him to be a stinky doo-doo head, and I think that wins in kid circles. I don't know. Seems to work in adult circles now. I mean, spend any time on social media, you'll find out that that's pretty much the level of discourse. People are pretty much yaha, nuh-uh, well, you suck. And it's like, wow, great. You know what I mean? And when someone's like, oh, well, you should do your research, what they're really saying is, you should do my research. Which is to say, don't research things, just agree with me, please. Because research sounds hard. You know what I mean? Usually when someone switches to personal attacks, the best thing to do is just say, oh, yes, I accept your defeat. I accept your surrender. I accept your surrender. Since you're switching over to ad hominem attacks, I assume that you cannot reject my arguments. Therefore, you concede. I accept. You owe me a Coke. So let's look at another example. Something that I declared yesterday would be convergent. Let's use the integral test to show that it is. Yesterday I made this claim, that the series 1 over n squared converges. The sum of all the reciprocals of the squares of integers converges. And we can use the integral test to do it. We'll find the integral from 1 to infinity of 1 over x squared dx. To calculate this limit, I have to calculate at infinity, I have to replace it with the limit as b goes to infinity. We can see here the important thing that's going to happen and why I care about the integral test so much and why I spend a whole day just yammering on about the integral test. We're going to see something very different happen in this antiderivative, and it happens right here. The integral of x to the negative 2 is minus x to the minus 1. When we integrate, the variable still shows up in the denominator. That's the thing that we want to notice. So we have a minus 1 over x evaluated from 1 to b. So notice that the antiderivative, in the antiderivative, the variable is still in the denominator. That's why 1 over x is kind of like the border between the two. If we have 1 over x to the more than 1, when we integrate, the variable is still in the denominator. So here, in the antiderivative, the variable is still in the denominator. The antiderivative has a variable in the denominator. That didn't happen with 1 over x. If we have 1 over x to the less than 1, when we add 1 to the exponent, it'll end up in the numerator. But if it's 1 over x to the more than 1, then when we add 1 to the exponent, the x is still in the denominator. So now we'll take the limit as b goes to infinity of minus 1 over b minus a minus 1 over 1. Now the minus 1 over b part, as b goes to infinity, the 1 over b goes to 0. One over 1 is just 1. And so our limit is equal to 1. So we can conclude, since the improper integral since the improper integral, the integral from 1 to infinity of 1 over x squared dx converges, the series one over n squared converges by the integral test. Calculating the improper integral in the line above is just showing that this improper integral converges. That's showing our work. I put in parentheses improper integral in the series because we would just say since the integral from 1 to infinity of 1 over x squared to x converges, the series 1 over n squared converges by the integral test. But I want to make sure we distinguish between the two things that are converging. The improper integral converges and the series converges. What you would not want to do in this situation is start trying to drop in pronouns. Since they converge, that's bad. And you also wouldn't want to mix your convergent with things that don't converge. You wouldn't want to say the limit converges because that's not something we say. We don't say the limit converges. You would probably get your point across for the most part, but it sounds, whenever I hear people say that, it sounds to me like saying you are driving a plane. That's just not the things that we put together. You'll get the point across, but that's not correct. You know what I mean? I'm piloting my car. That just sounds weird. Sounds like you're trying to do something weird and makes everybody suspicious. So don't say it that way. This is especially a no, I don't know if it's a problem, but this becomes especially prominent in the linear algebra class that I run this summer, where I pretty much at the beginning have to outlaw the use of the word it, because y'all keep wanting to say it converges, so it exists or something like that. It has a pivot in the rightmost column. Because then I'll be like, oh, what has a pivot in the rightmost column? And then you have to write out what you're talking about. You know, the augmented matrix for the linear system has a pivot in its rightmost column. And then I'll circle its, and I go, oh, what do you mean by it? And it's just pretty much stop using the word it. I'm not, in fact, a knight who says neat, so it's just, I just try to make the language clear. You know what I mean? So, takeaway for today is that we can determine if a series converges by looking at an improper integral. I guess the other takeaway for today is what an improper integral is. There's like a whole section on improper integrals. And you're like, oh, well, why didn't we do that section? And I'm like, oh, well, we just did, didn't we? So that's why I was just saving it for this. The bigger takeaway, other than the is what we can use or what we care about the integral test for. We can now see past the integral test, so we don't have to write out the integral test. And so if I write an integral, or if I write a sum of 1 over the square root of n as n goes from 1 to infinity, we can determine right away that this diverges. We can just look at it and see that it diverges. Think about the integral test. So the thinking that allows us to determine that this diverges real fast is the integral test. When I add 1 to the exponent, the variable appears in the numerator. The antiderivative has a variable in the numerator. And so when n goes to infinity, this will go to infinity and beyond. So it's very easy to determine if series converge or diverge by looking when they're in this form, when they're rational or radical functions. Yikes. The integral test has now solved for us all these rational and radical terms. Once we introduce the comparison test, which we will introduce tomorrow. So you might notice that we talked about 1 over n squared, but what if it was 1 over n squared plus 7n minus 5? Or 1 over the 5 plus the square root of n minus 7? What if there's other stuff going on? And for that, we're going to come up with, like I came up with these things, we will introduce the comparison tests. All right, that will be for tomorrow. So that will be it for today. Everybody have a good day. I'll see y'all on tomorrow, and thanks for playing.